Good morning, everybody, and welcome back to Linear Algebra. Plan for today is I have your first quiz of the semester on Standard 1, and then we're going to pick up where we left off last time talking about vectors and also potentially matrices today. I've got my usual office hours today and Wednesday at 11 and at 1, tomorrow at 1. I came up with some standard 2 problems that are kind of give you some practice on what we're going to be looking at this standard, and then I realized before class that I forgot to actually post them, so I'll post those later today on Canvas so you can get some extra practice problems. Plan will be though to finish up standard 2 on Wednesday with the idea of having the standard 2 quiz then on Friday. So, speaking of Friday, I apologize for missing class on Friday. Turns out I came down with a bit of a nasty cold, woke up Friday morning, decided no, I'm not teaching like this. They can have a day off. And apologize for that. I know how excited you all are to be here. I kind of built into the schedule the idea that one day I'm probably going to miss for some reason, like being sick. If we miss any more classes, I'll do something to make them up. Whether that be record a video on my own or give you all an activity to do outside of class. We'll figure something out. Yes?
If we retest this week for Standard 1, could we also retest for Standard 2 again this week? If we were going to retest for Standard 1 last week?
Yes. In that specific scenario, yes. Generally, I don't allow multiple retests in the same week, but if you contacted me last week to do a retest, say last Friday, and I end up not being able to make that for whatever reason, then yes, that you could do last week's retest this week in addition to this week's retest. So, it's quiz day. And I have a very important question for you all. And this is going to impact the rest of the semester. Would you all like the joke of the day before the quiz or after the quiz?
After. I need something to look forward to.
Today I can give you one of each. Because I owed you a joke from Friday.
Yeah.
But in the future there's only going to be one joke, so you have to pick one.
Can we determine that after the post-quiz joke?
Acceptable. Okay. So let's see, what's before? Which one do I want to do before? What is most commonly worn by mathematical mermaids? Algae bras. Okay, and with that, I'm going to pass out the quiz. So, quiz policies. Generally, I'll give you, I usually give like 10 to 15 minutes on a quiz, and I'll kind of base that off of looking around the room, seeing how many people still look like they're frantically writing. I'll also, when you're done with the quiz, just hold on to it. Draw a picture on the back for me. Draw a picture of something that makes you happy. And when you have about, at some point I'll make an announcement along the lines of, go ahead and take a few seconds to finish up your thoughts. That's Dr. Urstel lingo for you have about 45 seconds left, just so you know. And with that, any other questions before I pass out this quiz? All right, so you have a system of equations. I want you to solve it using Gauss-Jordan elimination. And keep in mind your solution could either be, oh, x, y, z has to be this particular point, or it could be there are infinitely many solutions or no solution. Keep that in mind. And I also do ask you for what is the reduced row echelon form of the corresponding matrix. So yes, you have to go all the way in this case. Have fun. There's a typo in the quiz on the second, which you may have guessed. The second equation should say 4x minus 2y plus 6z equals 0, not 4x minus 2y plus 6x equals 0. Sorry about that. That one was not meant to be a trick question. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Alright, I will get these graded and get them back to you on Wednesday. In the meantime, you are welcome to schedule a standard 1 retest if you would like for this week. And for those of you who did retest last week, I'll pass those back on Wednesday as well. So let's see, I don't know if you joke of the day, didn't I? Oh yeah, what type of math is most commonly discussed between seabirds? Type of math most commonly discussed between seabirds is intergull calculus. Okay, so do you all have thoughts yet on whether you prefer joke of the day before or versus after the quiz? It's always fascinating to ask this question to different classes because you never know how they're going to respond. Sometimes there's a strong opinion one way or the other. Sometimes it's like this one where it's sounds like there's a lot of indifference.
I think after is good. Yeah, I like after.
See, which is interesting because in my Calc 1 class there was a strong opinion for before.
I would say before.
But I also like
Let's put it to a vote then. All those in raise your hand. All those in favor of before the quiz.
Oh, yeah.
5. All those in favor of after. Okay, the afters have it. Try to even it out, but this makes my job harder. Okay, so rest of class today and Wednesday, we're going to be focusing on Standard 2 again, where we're not going to be row reducing any matrices for those of you who feel traumatized from what just happened. But what we are going to be doing instead is looking at properties of vectors, and then in Wednesday's class, matrices. How can they interact? What are they? How can they interact with each other? What are the different types of algebraic / geometric operations that you can do on them? So, does anybody need a copy of the Standard 2 packet? Does everyone have one? So, you may recall that, gosh, last Wednesday, it's been too long. We talked about the number system over which we're going to be working. Specifically, we said that vector in Rn is just going to be an ordered n-tuple of n real numbers. A1, A2, up through AN. So, n-tuple, we said, is just a fancy way of generalizing the term coordinate pair, where in R2, when we have 2 coordinates, we just call it a coordinate pair. In R3, we can call it a coordinate triple. In Rn, if we're not specifying what dimension we're working over, we just call it a coordinate n-tuple as a generalization of pair or triple. So a vector in R1 we usually just call R. A vector might just look like a single number, 2, 4. Technically, if you really want to, if you want to be really nerdy about it, you can make it a coordinate 1 tuple. But nobody actually does that. You just write it out as single numbers. In R2, we could write it out like 0, 1, or 1, 0. Are these the same vector? Why not? Yeah. Ordered in tuple means the order in which you write the numbers matters. So if you have the same two numbers, 0 and 1, but in a different order, that's not the same vector. In R5, for instance, we might have 1, 2, 3, 4, 5 over pi as a vector, etc. But for a fixed n, the vector in Rn is just made up of these sort of individual coordinates. And I think we also talked briefly about some different notation that we are going to use in this class. Specifically, bold-faced V versus V with a little arrow above it versus just a plain old V. And what did we say we meant when we had? I'm just going to answer my own question because I don't like my question already. We said that whenever you have a bold-faced like letter, like a V or a V with a hat over it, they refer to the same thing. They refer to vectors. What did we say when we referred? What did we call it when we just have like a plain old-fashioned V with no bold, no arrow above it, no fuss, no muss, no cocoa nuts? When?
A scalar.
Yeah, we call it a scalar. What's a scalar?
A number.
Yeah, scalar is just going to be, for the purposes of this class, for right now, a single number. Later on, when we get fancy in some later standards, scalars can be more than just single numbers. But for now, we're just going to treat it as being a single number. So for instance, you might say V equals 1, but if you want to refer to V as being a vector, like 1, 2, when you're handwriting, put a little arrow above it. Please, please, please do not use the boldface font unless you are typing. Otherwise, if you do something like this, I'm like, is that supposed to be bold? Is it not? I don't really care, but it's also ambiguous, and I don't like ambiguity in my, except in my own head. So please, stick to the little arrow notation if you're handwriting. And I believe that is where we left off last Wednesday. So, what I'm going to do today is talk about how can you take these vectors and combine them? Or how can you take these vectors and graph them? So look at them, so to speak. So for instance, let me on page 2 in the packet. How do we visualize, say, the vector -3, 5 in an R2? So in other words, if I were to ask you to sketch me a picture of what -3, 5 would look like, what would your first instinct be? Eleanor?
Make axes.
Make axes, okay. I have made axes. Do these axes represent -3, 5 in some way?
Not yet.
Oh, what else do I need to do?
You don't. Well, you can mark them and show where the numbers are.
Ah, so like that?
Yeah.
Yeah. So we could graph -3, 5 in the usual way and represent it as like a point right here. You have an x-axis, a y-axis. -3 is our x-coordinate, 5 is going to be our y-coordinate. You can either think of the vector as being one of two things. You could think of the vector geometrically as corresponding to the single point, -3, 5, going 3 units to the left on the x-axis in the negative direction, and 5 units in the positive y direction. Or you could think of it as being an arrow that points from the origin to -3, 5, and say that -3, 5 corresponds to this arrow. And depending on the situation, it may make more sense to think of it as being a single point or as an arrow. Typically, if you want to think about what does it geometrically mean to add two vectors in some way, it oftentimes makes more sense to think of it as an arrow pointing somewhere rather than as a single point. So I'll just make a note for now and say the vector v equals -3, 5 can be thought of as a single point or an arrow from the origin to that point. Any questions or comments about that? So let's go up a dimension. How would we graph something in R3? If I wanted to say visualize the vector 3, -1, 4 in R3, suddenly our plain old x and y axes aren't going to be enough, because we'll have an x coordinate, a y coordinate, and a z coordinate this time. So how do you think we would try and draw a picture of what 3, -1, 4 might look like?
A three-dimensional grid.
A three-dimensional grid, indeed. So we're going to have an axis going up and down. We'll have an axis going left and right. And we'll also have an axis that's going to jump out of the board at you. So typically our z-axis, this is going to be the vertical one, we'll have going up and down. We'll have a y-axis that points left and right, and an x-axis that corresponds to depth. Now, I'm trying to draw a three-dimensional grid on a two-dimensional blackboard. Obviously, there's going to be some information that's lost in translation, because you can't really accurately draw in 3 dimensions on a 2-dimensional surface. So instead of having this x-axis going from like up right to down left, the way you're supposed to think about this is the x-axis is going out in the positive x direction, in, so like back into the board in being the negative x direction. And you're thinking of this, and you're kind of looking at this from a bit of an angle. Instead of looking at it dead on where the x-axis is coming out and punching you in the nose, you're kind of standing a little bit over to the side and looking at it from like a 45-degree angle between the x and the y axes, let's say. But the idea is we have 90-degree angles here, here, and here. And that there's, just like in the xy plane in R2, there's 90-degree angles, right angles between the x and the y axes. We want to think of there being 90-degree angles between all pairs of xy axes, xz axes, and yz axes in R3. And once you have once you have your axes all labeled, graphing works the same way as you might expect. You go out 3 units in the positive x direction. 2, 3. So think of that as being 3 units out of the board coming at you. 1 unit in the negative y direction, so to the left. And then 4 units straight up. 1, 2, 3, 4. In. Now there's a problem that if I didn't label the tick marks and just drew this point right here, Do you know that that point corresponds to 3, -1, 4 without the tick marks?
No.
I would say not. It could just as easily be x equals 0, y equals -3, z equals 3 or something, say. So something that's often used to help distinguish is something like little dotted arrows. So like, actually let's put it over here then. Basically say, hey, you're going out 3 units this way, 1 unit that way, and 4 units straight up. You can sort of have little dotted marks like that to kind of help illustrate how you get from the origin to your point in space. And then, just like in R2, we can either think of the vector 3, -1, 4 as corresponding either to the point itself in space, or as an arrow pointing from the origin to that point. And again, as we'll see going forward, depending on the context in which you're looking at or thinking about your vector, it might make more sense to visualize it in one way as opposed to another. How do you think we might visualize a vector in R4? Yeah, I would say there's either 2 answers to that question. The first answer is you don't. And R5 and higher similarly. Alternatively, you could think of R4 as being like 3 dimensions, but your 4th dimension then just corresponds to time. So you could have 3 dimensions changing over time, and the point 3, -1, 4, 6 might correspond to something like, oh, I'm going to come 3 units out of the board at you, 2, 3, 1 unit in the negative y direction, 4 units straight up, pretend like I'm ascending through the air, and then 6 corresponds to, it took me 6 seconds to do all of that. So it's 6 seconds after I started, that's where I'm located. That's one way you could sort of try and intuitively think about a vector in R4, having like 3 coordinates correspond to location in 3-dimensional space and 1 dimension corresponding to time. Or you could just say, I'm going to treat this as an algebraic vector and not worry about it. But yes, trying to draw that in a 2-dimensional picture would be most challenging. I would want a computer animation, and even then, some information would be lost, so to speak. And I guess maybe I should have mentioned in R1, how do we visualize a point? I don't know, draw number 1. Most of the pictures I draw in here, and then I'll make you all draw, are going to be in R2 for reasons of R1 is boring and R3 is hard and R4 and up is kind of impossible. But I do want you to kind of have, when we talk about these different types of vectors, I do want you to be able to kind of have intuitive images in your head of what's going on, how does the dimension in which we're doing our computations correspond to some sort of physical picture whenever possible. Any questions or comments before we start talking about our algebraic manipulations? In that case, there's 2 basic operations we're going to be looking at with regards to things you can do to vectors. That being the idea of vector addition and vector scalar multiplication. So, be on the 3rd page now. So with vector addition, if we have 2 vectors in the same Rn, we can add them together and say that if vector v is v1 up through vn, notice that v is a vector, so I'm putting a little arrow above it, but v1 through vn are all scalars, so they don't get arrows or bolded or whatever. And we have another vector, w, that is equal to w1 through wn. and these are both vectors in the same Rn, algebraically, how do you think we would find a formula for the new vector v plus w? In other words, what would intuitively make sense for you to say that we need to do in order to add the two vectors?
You would add the components.
Yeah. The first coordinate is just going to be the sum of the first component of the original two vectors, so v1 plus w1. Second component is you just add the corresponding components of the original two vectors. And et cetera, et cetera. You just work your way down the line. But the point is, v plus if you have two vectors in the same Rn, you can add them together to get another vector in that same dimension, in the same Rn. The other operation you can do with a single vector and a scalar is scalar multiplication. Where if v is a vector in Rn, v1 through v sub n, and r, did I call it r in the packet? I did indeed, is a scalar, we can multiply a vector by a scalar, which we usually just write as being like rv, like this. And what do you think it would mean intuitively to take a vector, something with n components to it, n coordinates, and multiply by a single scalar value, by a single real number?
You multiply each component by r.
Exactly. You just take each coordinate of your vector and multiply by that scalar using plain old real number multiplication. So it'll be r times v1, r times v2, all the way up to r times v sub n. And these are the primary operations that we'll be doing algebraically that involve manipulating vectors and scalars. Is take two vectors, add them together, take a vector, multiply by a scalar. But Dr. Gerstle, what about multiplying two vectors together? We'll talk about that as well here in a few minutes, but that one's a special case because it doesn't do what you might necessarily think it does, unless you've already taken Math 420. So as a quick example, let's say I wanted to take 3 times the vector 1, 2, 3, 4 and add that to 5 times the vector 2, 3, 0, negative 6. So this would be doing something that is a combination of adding vectors as well as doing some scalar multiplication. What do you think we should do first? Here we sort of have some order of operations going on.
I would say do the scalar multiplication first.
Yeah, just like how if I gave you something like 3 times 1 plus 5 times 2, you would do the multiplication first. You take 3 plus 10 is 13. The same holds true when you're doing combinations of these operations on vectors. You do the scalar multiplication first unless you have parentheses that tell you to do otherwise. So we took 3 times the vector of 1, 2, 3, 4. What would that give us?
3, 6, 9, 12.
It would indeed. And 5 times the vector 2, 3, 0, negative 6.
10, 15, 0, negative 30.
10, 15, 0, negative 30. And now that we've done our scalar multiplication, we can add our two vectors together to get 13, 21, 9, negative 18. And that would be a way of taking two vectors in R4 to start, multiplying each of them by a scalar, and then adding the corresponding R4 vectors together that we get to get another vector in R4. So something to keep in mind. 3 here is an element in just plain old R1. This is a vector in R4. Similarly, this is in R, this is in R4. And whenever you multiply a vector in Rn by a scalar, you're still going to get a vector in the same Rn. And if you add two vectors in the same Rn together, in this case R4, you'll get back a vector in that R, in that same dimension. Questions, comments, or things? So, what about if I tried to add the vectors 1, 7, 5, and 3, 8?
Well, you can't, because they're not in the same dimension.
You can't. That doesn't sound like a very positive attitude to have.
Could you theoretically convert 3/8 into a 3/8,0?
Ooh, embed a two-dimensional vector in three-dimensional space. Theoretically, you could. But practically speaking, we're not going to. Well, no, I'll double down. Practically speaking, we're not going to and say, this is in R3, this is in R2, and vectors have to be the same dimension in order for you to be able to add them together. If you were to hold a gun to my head and force me to add these vectors together, that's probably what I would do. Is I would say, all right, 1 plus 3 is 4, 7 plus 8 is 15, 5 plus nothing is 5. But practically speaking, we don't generally talk about adding vectors in one dimension to vectors in another dimension. You can force it if you really want to, but in most of the contexts we're going to be looking at, it wouldn't really make sense to. So, when we do vector addition and scalar multiplication, that's oftentimes called doing a combination of those things, taking a linear combination of those two vectors. So in general, you can say that if v sub 1 through v sub k, if you have k vectors in Rn, and scalars R1 through R sub k, then any expression where you multiply your vectors by scalars and add them together, so any expression, in other words, of the form R1v1 plus R2v2, not R2d2, exactly, plus RK v sub k, is called taking a linear combination of your vectors. And since the word combination has too many letters in it for my taste, from here on out, if you see me write combination on the board, I'm just going to write combo and leave it to you all to interpret what that means. Of v1 through vk. So in general, taking a linear combination of vectors means multiplying by scalars, potentially. If you don't want to change it, you can just multiply by the scalar value 1, and then adding them together. And I mention this now because linear combinations is going to be like one of the biggest things we look at this semester. Not like how do you take a linear combination algebraically, because that's pretty easy, but different ways to interpret when is one vector going to be equal to a linear combination of two other vectors? It's going to be a big question going forward. And it's going to get us into concepts like spanning sets, bases, and linear independence, and all that jazz. Questions, comments, concerns? Well, you look like you have something you're stewing over.
Just looking at it, thinking it over.
Yeah. I realize we're going really quick through this. This standard, for one, this standard's, as you can probably guess, is going to be a lot less computationally intensive, at least until the end, than the previous standard. For another, I'm guessing you all have seen a lot of these ideas before, and are maybe just kind of, need some illustration in a new light, or putting them together in the context of this particular class. So that's actually going to do it for today. When we come back on Wednesday, we might actually need Friday to finish this standard. When we come back on Wednesday, we're going to talk about a couple more things related to vectors, namely the dot product and magnitude, as well as to start doing some similar sorts of ideas looking at matrices. And then that'll finish up Standard 2 for us. I'm guessing Standard 2 is probably not going to be finished until Friday's class. We will get there. Alright, with that, hope you all have a good rest of your day. I'll see you all on Wednesday. Sorry again about Friday's class.